I'm a binary in a binary world.
Um,
Ones and
hey,
zeros. That's
did I catch you at a
fantastic.
bad time?
Oh, hey, no, not at all. It's the perfect time to enter the world of binary digits or bits, and we never speak of this again. Machines speak ones and zeros, but why? Why don't they speak English or Chinese or Italian or Spanish? Using a human language has so much ambiguity in it and literally no consistency. Just due to the different variations that can be there anytime someone says hello or someone goes and says, hey, yo, bro. And there's so many different ways to say the same thing and do the same thing. And computers are pretty dumb. You've got to realize that.
But but what about AI, you may ask? Even the most complex AI are just rocks and minerals we have tricked into thinking by making electricity pass through them.
Keeping this matter of consistency and to reduce vagueness in mind, machines need a very simple to understand mode of communication. Humans, most of us anyway, deal with the positional basin system, whether it comes to matters of money or time or any other representation that we're doing. We have only 10 ways to represent a number. So we've got 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. And I just took you back to grade school. And the reason I took you back is that to represent any number from 0 all the way to a gazillion, we just need a different combination of these 10 numbers. So what's actually happening? Again, I know most of you would know this from grade 1, grade 2, and grade 3, but let's look at place value. The place value of the number changes. So here I have 3,214. Each place is a multiple of 10. So the first one, 4, is a ones place, then 1 is a tens place, 2 is a hundreds place, and 3 is a thousands place. The overall value is gotten by summing up the values multiplied by the digit in that position. Computers actually use something called as binary, which is a positional base 2 system. What does it mean to be a base 2 system? So that just means you have 0 and 1 instead of 0 all the way to 9. Every 2 counts in the place value system, we increase by 2. And what does this actually look like? So we have 0 and 1, as always. Then we have 10, which is actually read 1, 0. And then we have 1, 1. Then we get 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, and 1, 0, 0, 0. What this means is that every time you go to the left in the place value system, you're multiplying by 2, and you get a different combination of a 0 and a 1. That's it. You cannot have any more digits. Get this through your head. We have binary 2 to actually match the electronic capabilities of the transistors that we mentioned all the way back in the starting from the bottom videos. Transistors were rising in prominence during the business logic started getting really popular all over the world for all sorts of applications.
Well, starting from the Victorian era, the time of vampires and Van Helsing and whatnot, with mechanical hand-driven calculators, the question was, how do you grind 10 counts easily? The days of Charles Babbage, power-hungry systems, mechanical vacuum tubes needed fewer digits and simple to build machinery. Of course, this means 3.322 times the circuitry would be needed than a base 10 to capture more. But they are simpler, so the trade-off is worth it.
Interesting point there. Eh? Let's see how you can come up with the exact same solution. Let's say I have a bulb in my house and I want this to light up. I'm starting with a counting system of just 1. That means I would just have 1 digit, which is 0. What states can I represent? Well, I can only represent 1 state because I only have 1 digit. And this means that I can say this is either off or either on. But if off is 0 and on is also 0, then up is down and down is up, and what is even happening? So let's move on. Next up is the counting system of 2. I start off with a 0 and then I add another 1. That's it. Now I have 2 states to represent one thing. I can use 0 to represent off and I can use 1 to represent on. We can also switch that around, but most of the time 0 means off and 1 means on. And with that, you get the simplest way to represent a situation. And that's basically it. And that's how transistors work. We have off and we have on, 0 and 1. Now let's see what happens when you keep 2 voltage levels. What are the other advantages that you can have? One is that it becomes more reliable and resistant to noise and other electrical interference. So you just fluctuate between 0 and 1. You don't really go to other places, making it harder for the computer to guess which value you are at. And we can do this without using too much additional power and needing additional equipment and so on, and keep it pretty smooth. So think of it like this. We have a positive voltage and a relative negative voltage. All the time, transistors operate between these two stages to go either on or off.
New computers can reference 16 digits, 255 to 65,535 digits, 8-bit to 16-bit to 32-bit. The more representations you can have, the more computational possibilities there are.
And thank you, and I'll see you in the next video.